Alright guys, so in this chapter we're dealing with the electric potential and its relationship to the electric field. And specifically in this video we're going to talk about how to find the electric field from the electric potential information. So let's assume that we have a region of space that we have mapped out. We have at all of these different points we have figured out the electric potential. And moreover, we know that all of the points connected by a line have the same electric potential. So along these lines, the electric potential is constant, and we have labeled the electric potential as you can see there. Now, the idea would be to use this information about the electric potential to figure out what is the electric field and the little red dot that I drew there in between the 10 volt and the 20 volt equipotential. What is the electric field vector? So one way to start this calculation is to take a look at the difference in potential between point 1 and point 2. Notice that I chose 1 and 2 to be horizontal, one to the right, one to the left of the point of interest. So the difference in potential between 1 and 2, our basic equation discussed before, says that the difference in potential between 1 and 2 should be the negative of the integral of the electric field dot product with the displacement vector. So if we assume as an approximation that the electric field is more or less constant between 1 and 2, that the electric field at point 1 is not very different from the electric field at point 2, then we can, instead of doing the integral, we can simply, as an approximation, take just the dot product between E and the vector delta S, where delta S is the vector that goes from 1 to 2. From point 1 to point 2, you can see that it's a horizontal vector. That means that it only has a x component. So we can write delta S as the number delta x times the I hat vector, the unitary vector that points in the x direction. That's standard notation. So putting that into our equation, we see that we're doing the dot product between E and delta x times I hat. And this results in delta V between 1 and 2. It will be negative of Ex, the x component of the electric field, times delta x. That's because the dot product between any vector and the vector I hat is equal to the x component of the vector. That's the definition of the vector I hat. So we see that by taking the voltage at points 1 and point 2 and dividing by the distance between point 1 and point 2, we can get the x component of the electric field. If we do that, then with a negative sign in front, the difference in potential between 2 points located horizontally to the right and to the left of the point of interest, that's what I mean by putting the x next to the delta V, is that the 2 points that we're evaluating are horizontal. So that gives us the x component of the electric field at the point of interest. Right? So we're interested in finding the electric field at that point. If we take 1 and 2, like that, then the difference in potential between 1 and 2, and that divided by the distance between 1 and 2, with a minus sign in the ratio, the delta V minus delta V over delta x is the equation. Don't forget the negative, which is actually pretty easy to forget. That number will give us the x component of the electric field at that point. So of course, the electric field could have another component, the y component. So to do that, what we're going to do is we're going to select 2 points, one above, directly above, and one directly below the point of interest. We're going to label those 3 and 4, and then we proceed the same as before. So we're going to look at the difference in potential between point 3 and point 4. The equation says that that should be approximately equal to the negative of the electric field dot product with delta S. Our delta S vector is a vertical vector, so we can write it as delta y times j hat. So because of that, the dot product is going to give us the y component. It's going to be minus the y component of the electric field times delta y. So similarly, the y component of the electric field then the result for that y component would be minus delta v divided by delta y. Okay, so using calculating that number, we get the y component of the electric field at the point of interest. So this calculation gives us that component. The other calculation for Ex gives us the horizontal component of the electric field, and the electric field obviously is the vector that has x component Ex and y component Ey. All right, let's put in some numbers here. So let's say that the vertical distance between points 3 and 4 is 1 meter, and that the horizontal distance between 1 and 2 is 0.5 meters. So if that's the case, then the x component of the electric field would be negative, and then 20 volts, because that's the electric potential at point 2. Notice that that point 2 is on the 20 volt equipotential, minus the electric potential at point 1. Point 1 is on the 10 volt equipotential. So the equation says minus, and then delta V, which in this case will be 20 volts minus 10 volts, divided by the distance between 1 and 2, which is 0.5 meters in this example. So that gives us, the numerator is 10 volts, so minus 10 divided by 0.5, which gives us negative 20 volts per meter. So we know that the x component of the electric field is negative in this example, and it is minus 20 volts per meter. All right, for the y component, we must look at the difference between points 3 and point 4. So point 3 is at 20 volts, point 4 is at 10 volts, so 20 minus 10, and divided by the distance between those 2 points, which is 1 meter. So for the y component, we get minus 10 volts per meter. So the electric field vector, evaluated at the point of interest, has an x component that is negative 20, so it points to the left, and it is 20 volts per meter in magnitude, and the y component is negative, which means that it points downwards, and in magnitude is 10 volts per meter. So our vector points to the left and down. Notice that that is consistent with what we already know about electric field vectors, which is that they're always perpendicular to the equipotentials. Also, we know that the electric field direction is from high voltage towards low voltage. That's exactly what we got here. The electric field is pointing from the high voltage towards the low voltage equipotentials. All right. Now, if you were interested in finding what's the magnitude of the electric field in this example, then you will take the x component and the y component and use Pythagoras' theorem to figure out what's the magnitude. That would be the square root of minus 20 squared plus minus 10 squared, and that will give you 22.36 volts per meter. If you wanted to know the specific angle at which the electric field vector is pointing, then you will do the angle is the inverse tangent of the y component of a vector divided by the x component of the vector. So in this case, inverse tangent of minus 10 divided by minus 20. That will give you 26.6 degrees. But remember that whenever using the inverse tangent, you have to be careful because the answer might be off by 180 degrees, which is the case here because 26.6, remember that that is measured from the positive x direction, and that would be in the first quadrant, but our vector clearly is pointing in the third quadrant. So we need to add to this 180 degrees for a final answer of 206.6 degrees. All right, now let's take a look at a different way of doing this kind of calculation that might be simpler depending on the information given to you. So if we have an electric field pointing in some direction, and we move from point 1 to point 2, I'm calling that our vector delta S. So the difference in potential between point 1 and point 2, per our equation discussed before, is, as an approximation, it would be minus E dot delta S. Now the electric field vector, you can decompose it into the component pointing along the S direction and the component perpendicular to it. So the dot product between those two vectors can actually be written as minus the S component of the electric field multiplied by delta S. Only the component of a vector parallel to another one is the one that contributes to the dot product. So that means that the difference in potential between those 2 points divided by the distance between them with a minus sign will give us the component of the electric field in that direction, in the direction defined by the 2 points 1 and 2. So we can use that for this kind of problem that we looked at before, that we just calculated in the previous problem. But we could use that if the information given to us had not been this vertical distance and the horizontal distance, but more typically in a problem like this, with this kind of equipotentials, more likely you will be given the distance between the equipotentials, or maybe you can measure them from the figure. So if that is the information that you have, distance between those equipotentials, then this equation comes in handy. What you need to do is choose S to be the direction perpendicular to the equipotentials. We already know that the electric field should be pointing in that direction, and from high voltage to low voltage. So we already know that the electric field points in that direction. So that should be our S direction. So the equation evaluated along that direction, to use the equation in that direction, we're going to pick points 1 and 2 along that direction. So we're going to look at the difference in potential between 2 and 1. So that is 10 volts minus 20 volts. So the difference in potential is minus 10 volts. The distance, as I said, you were given that distance, so it's, let's say, 1 centimeter, so 0.01 meters. And all we need to do is use the equation. The component of the electric field in the S direction is going to be the same as the magnitude of the electric field, because notice that we already picked the S direction to be the direction in which the electric field is pointing. So plug in the equation, minus delta V over delta S, minus, and the delta V is minus 10, so minus 10 volts divided by 0.01, and that gives us an electric field component in the S direction of 1000 volts per meter, but that is the same as the magnitude of the electric field, 1000 volts per meter for this calculation. Now, we have been using this equation, and we have been saying that this is an approximation, that if I want the X component of the electric field, it would be obtained by approximately taking, as an approximation, taking negative delta V over delta X. The question that I want to briefly discuss here is, how do we make this an exact, how do we calculate exactly what is the X component of, say, an electric field, given information about the electric potential? So how do we make that an equal sign instead of an approximation? The idea is that we will have to take the limit when delta X goes to 0, because remember that when we obtain the equation delta V over delta X, we assume that the electric field was constant between those 2 points that we chose. So if the electric field is not constant, what we have to do is take the limit when the distance between the 2 points goes to 0. That's the only way to guarantee that that electric field is not going to change much as you go from one point to the next. So we're taking the limit when delta X goes to 0 of minus delta V over delta X. That limit has a name, as you know from your calculus classes. This is the derivative of the electric potential with respect to X in this case. Now notice that I'm writing this derivative in a funny way. Instead of the regular D, I'm writing this D that is a bit curved, and that's because this is the notation that we use in math for partial derivative. The idea is that the electric potential is a function. It depends on, in principle, 3 coordinates in space: the X, the Y, and the Z. So what we're doing here to calculate the X component of the electric field is to take the derivative of that function, but only with respect to X. So the Y and Z variables in your equation are going to be treated as constants when we take the derivative of the function with respect to x. Similarly, for the y component of the electric field, we need to take the limit when delta y goes to 0, and that gives us the equation negative partial derivative of the electric potential with respect to y. Again, if the electric potential is a function of x, y, and z, when we take the derivative, we assume that x and z are constants. And the same for in 3 dimensions to get the z component of the electric field. In which case, we will take the x and the y coordinates to be constants. Alright guys, that's all I have for now. See you in the next one.